Hey guys, I'm Spencer.
I'm Jason, and today's video is on making solutions
Of a given pH.
So today let's talk about making solutions of a given pH. And we'll look at some of these ideas, and we'll start with a strong base. So let's look at this problem here. We want to make 2 liters of a pH 11 solution, and we'll make that from strontium hydroxide, solid strontium hydroxide. So the question is, how much solid strontium hydroxide do we need to use to make 2 liters of this pH 11 solution? So here's a way to go about this problem. It's pretty straightforward. We'll just solve it right here. The first thing to notice is, of course, pOH equal 14 minus the pH, so pOH is 3.0. Therefore, the hydroxide ion concentration is 10 to the minus 3.00 molar, and that gets us 1.0 by 10 to minus 3 molar concentration for the hydroxide ion. Now a little bit of straightforward unit analysis here. 2 liters of solution. In every 1 liter, 1.0 by 10 to minus 3 moles of hydroxide ion. Remember that we get 2 moles of hydroxide ion for every 1 mole of strontium hydroxide we dissolve, and that every 1 mole of strontium hydroxide has a mass of 121.6 grams. Do all this, make sure you check the units before you finalize your calculation. We do get grams of strontium hydroxide here. That's 0.122 grams, but of course this has just 2 sig figs. Notice they're after the decimal place in a pH. So this here comes up as 0.12 grams of strontium hydroxide. Not much strontium hydroxide needed to make a pH 11 solution, 2 liters of it. Now let's look at a weak base. This will look a little bit different. And we'll make 350 milliliters of pH 8.5 solution from potassium fluoride. Now you have to think about that for a second. Potassium fluoride doesn't strike you as a base immediately, but we realize that it is in fact fluoride ion that's the conjugate base of hydrofluoric acid. So here we have the fluoride ion, and I'll do this hydrolysis with water, getting its proton making hydrofluoric acid and hydroxide. We'll need the Kb for this fluoride ion, which is of course Kw divided by Ka for the conjugate acid, namely hydrofluoric acid, whose Ka we look up and find to be 3.5 by 10 to minus 4. So putting in the values, here we have Kw, and on the bottom 3.5 by 10 to minus 4. And here we get the Kb for fluoride ion, which is 2.86 by 10 to minus 11. It's quite a weak base. Anyway, here's our solution. We'll need the pOH equal 14 minus the pH, so that's 14 minus 8.5, we get 5.5 here. And the hydroxide ion concentration from this will be 10 to the minus, of course, 5.50, which is, if you calculate, 3.16 by 10 to the minus 6 molar. Now this is a weak base, so it's coming from an equilibrium system, and we'll use an ice table to calculate that. Here again is our equilibrium reaction, and here we have the ice table. Remember that liquid water has no concentration for us, so we know the equilibrium concentrations of hydroxide ion from above. There it is, 3.16 by 10 to minus 6. It's in a 1-to-1 ratio with hydrofluoric acid. Those are the same, so we're going to add both these on the right-hand side. We'll subtract that same amount from the left, also in a 1-to-1 ratio, and it's that initial concentration of fluoride ion that we need, X there in the orange box. At equilibrium, will be X minus the 3.16 by 10 to minus 6. Writing down the Kb expression now, we have products over reactants, and this should be equal to 2.86 by 10 to minus 11, which we worked out before. Putting in now the concentrations for hydrogen fluoride and hydroxide on the top here in yellow, and on the bottom the fluoride ion concentration, which is in blue, as X minus 3.16 by 10 to minus 6. So X is our fluoride ion concentration. It's the initial one, the one we're after, and that is, if you calculate this, 0.349 molar of fluoride ion before the solution comes to equilibrium. So how do you get 3.49 molar fluoride ion? Well, it's 0.35 liters of solution. In every 1 liter, there's 0.349 moles of fluoride ion. It's 1 fluoride ion for every 1 mole of potassium fluoride. And finally, 1 mole of potassium fluoride costs you 58.1 grams of potassium fluoride. Check the units and the species. They all work out with grams of potassium fluoride. It's good, and it's 7.1 grams of potassium fluoride that are needed to make the solution. Quite a lot of it, interestingly enough. So anyway, that was strong bases and weak bases, and strong acids and weak acids, of course, work the same way, except you don't need to do that pH plus pOH equal 14 business. So if you just leave that out, then the strong acids and weak acids work the same as you've seen here. Thanks, everyone. That's got to be enough for today. I'll see you soon. Do be sure to have a look at the next 2 videos in our playlist, and stay tuned for the next lesson, lesson 20, mixing acids and bases.
This is my dad's YouTube channel. It's awesome. So like, comment, and subscribe!